Are you here, Noller? Maybe that's why I wasn't recording, because James wasn't here to remind me. Let's see. Oh, no, he is here. Or at least he's on. Okay. Well, if you're just turning on this YouTube recording, what you missed was Mr. Smith showing up about 10 minutes late and then sprinting through a re-explanation of the first half of example 3. And now we're going to very neatly take off or start off where we took off yesterday, with this Riemann sum being turned up to infinity. Okay, and so we're still kind of just ignoring the turning it up to infinity, because this is kind of capturing our attention right now. This Riemann sum that we have had now, I'm sorry, this is just a sum. That's, well, it's a Riemann sum too, but this sum that we've had some experience with in terms of simplifying because of some of the formulas that we've been given. So at this part of our process, this is where we're going to put those formulas 1, 2, 3, or 4 into play to come up with some expressions here. Now, a key step here, and I'm realizing this should be n cubed. And you don't have to do this at this step. For me, I like to do it here just to keep it kind of clean. Again, for now, just ignoring the limit, because as far as we're concerned, it doesn't matter until we've dealt with this sum.
Mr. Smith?
Yes.
Why does it say 2? Why is there a 2 next to the I squared?
There shouldn't be. It was
okay.
Me not crossing it out. So again, for now, we're going to ignore this limit. And we're going to look just at this sum that starts at 1 and goes to n, and whose index is I. Meaning the only thing that really gets affected by this sum are the i's, okay? This says plug 1 in for I, see what you get. Then plug 2 in for I, see what you get, add that to what you found for 1. Then plug in 3, then plug in 4, then plug in 5, until you get to n, whatever n is. We know what n is going to be because we know that we're going to turn it up to infinity. But at this point in our process, it's just some placeholder. And so as strange as it seems, this guy right here, 27 over n cubed, is in no way affected by this sum. Okay, I'll say that again. This 27 over n cubed is in no way affected by the mechanism of this sum. This is just a constant value of whatever n is. Okay, so if this was from 1 to 10, you plug in a 10 for n, this would be 27 over 1,000, and this 27 over 1,000 would be at every step from 1 to 10 of this sum. But the actual individual terms of the sum are only dependent upon I. So what that means is we can treat this like a constant and pull it out in front of the sum. Okay, that's a total legal move based on the theorems that we've seen, and just based on our knowledge of math, that if 27n cubed is going to show up in every term of this sum, whatever n is, then we can just factor that out. So we could do it that way, where we just keep it in here for every term and then factor it out, or we can just do it at the beginning. Okay, and so that's what we're going to do, is we're going to write this as the limit as n approaches infinity, which we still are kind of ignoring here, times 27 over n cubed, because this is just a constant, times the sum from 1 to n of I squared minus 2i plus 1. And now, just looking at this sum, this is just like example, I think, 19 from your homework a couple nights ago. This is something we can break apart and apply some formulas to and come up with some expressions involving n. And then is when we start to worry about the limit. So basically, we're going to turn this into something that only involves n's, hit it with the limit, and see what's left. And what's left will be the area under that curve. Okay, so trying to keep track of the different processes here. This is the sum. The limit will not come into play until we've dealt with all of these sum situations. So to do that, we're going to use those formulas on page, let's see what page that was. Formulas on page 349. And we're going to break this apart. This is 27 n cubed times, no, we're going to show the intermediate step where we break this into 3 individual sums. This will be the sum from 1 to n of I squared minus 2 times the sum from 1 to n of I plus the sum from 1 to n of 1. And now we evaluate each one of these separately. The limit, n approaches infinity, 27 over n cubed. This first sum of I squared, we look to formula 2 and use this quotient. That turns into n times n plus 1 times 2n plus 1 divided by 6 minus 2. For this sum, we're going to use formula 1 from 349. This guy here, n times n plus 1 divided by 2. And then for this final sum, yeah, there's a theorem, but we'll also just use common sense. If we're adding up 1 n times, what's the result going to be there? 1 plus 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 1 n times. Somebody. N. There we go. Cool. And now we are at the step where we're going to basically just simplify the crap out of this. Hope that there's some stuff left after we multiply through 27 over n cubed, and then hit it with the limit. Okay, so we're still not quite at the part where we're ready to hit this with the limit because we've got n's in way too many places. We'd end up with infinities everywhere and no real idea of what's happening. So we need to simplify this until we can maybe separate out some quotients that have n as their denominator, because where we're eventually headed is to a bunch of expressions with constants over n or n squared or n cubed, which will go to 0, and then some stuff left, which will be our area. So let's simplify this. The limit as n goes to infinity of 27 over n cubed. I'm sick of distributing this out. Let's see what that is. 2n cubed plus 3n squared plus n. Over 6 minus 2n squared minus 2n over 2. plus n. Kind of your choice here, whether you want to make this one big fraction or just distribute across each of these fractions. I say let's make it one big fraction. So we need a common denominator of 6. And so this will become the limit as n approaches infinity, 27 over n cubed times, this guy's okay, so this becomes 2n cubed plus 3n squared plus n. This guy needs to get hit with a 3 over 3, and so this becomes negative 6n squared. This becomes negative 6n. And then this n needs to get hit with a 6 over 6. So this becomes a plus 6n, all divided by 6. So it's pretty dang important that we're getting these coefficients right, because if we don't, we'll get the wrong answer. So being very careful with your algebra here and your simplification, making sure that we're doing this correctly. Still not quite ready to hit it with the limit yet, but we're getting there. The end is in sight. So let's clean up this quotient. We've got 2n cubes. My n squared terms combine into negative 3n squared. And that's kind of nice. Those go away, and I have an n left. Does that really work out? Sure, why not? All divided by 6. And now the big finish. Postpone. I do not want to restart my computer. So I'm going to do two things. That's really just one thing. I'm going to swap these. So I'm going to take this 1/6 out and simplify 27 over 6. And then I'm going to divide each of these parts of our numerator by n cubed. Or actually, let's just show that, because this is kind of the crucial step. So if we have successfully simplified this fraction, this is where we should get to our answer. So we have 27/6 times 2n cubed minus 3n squared plus n divided by n cubed. This 27/6 has absolutely no bearing on our limit because there's no n involved. And furthermore, we're going to call it 9/2. And so we're going to call this 9/2 times the limit as n approaches infinity, and then divide out each of these terms. So there's a limit as n approaches infinity of 2n cubed divided by n cubed is just 2. Negative 3n squared divided by n cubed is negative 3 over n. And positive n divided by n cubed is 1 over n squared. Oh, this is nice. What happens to both of these things as you turn n up to infinity?
It becomes 0.
It becomes 0. And so now we finally apply this limit. And what we find is that we get, let's do it big, 9/2 times the limit as n goes to infinity of 2 is just 2. This limit goes to 0. This limit also goes to 0. and then multiplying this out, we get that our area is 9 units squared. Whoa, Mr. Smith. Are you telling me that anytime we want to find the area under a curve, we have to go through that entire process? I'm telling you that for the next week of your life, yes. Yes, you do. There's a kind of unique satisfaction that comes from doing a almost 2-page problem, right? Yeah, there's a lot of steps. Yeah, it's not the easiest thing you've ever done. But at the end of it, you get this nice, clean 9 units squared. Okay, questions about that finishing sprint? Because this is kind of where the calculus happens. So we did the Riemann sum, and then at the end, really only that last step is where we turned it up to infinity.
I have a question about the beginning.
Yeah.
How did you get delta x cubed?
Good question. And that's a very important step. So it was in this changeover from the I minus first index of x. Well, that's not a terribly useful thing to plug into our function. We need to have it in terms of i's, really, or delta x's, or something we can actually use. And so we had to make this determination that the I minus first index of x, since our initial x index was 0, would be 0 plus I minus 1 delta x's. Because our first value here was x sub 0, and so 0 plus no delta x's get you that. Our second one was going to be at x sub 1, so that's 1 delta x away. So when you plug in a 2 here, that gets you 1 delta x away. When you need the third triangle, you need to be 2 delta x's away, and so on and so forth. And so what we ended up plugging into our function, which in this case was x squared, was I minus 1 times delta x. Because that's basically what our function value is at each step of this Riemann sum. Some amount of delta x's away from 0. And so then squaring this quantity gave you a delta x squared in addition to this binomial being squared, which is where the fun stuff with our sigma notation came into play. And so I guess I didn't explicitly show the separate step here where there was a delta x squared that combined with the delta x that came all the way from the beginning as the base of our rectangles. That first delta x combined with this delta x squared to make delta x cubed. Okay. And so that's going to be kind of a mainstay of this process, is that delta x is going to show up when we actually plug into our function.
Thank you.
Yeah. Okay, so that was a left-handed. We're going to do that same problem, but now use a right-handed sum. How do we want to do this? Do we want to recreate this whole thing? Yeah, might as well. Okay, so fresh page, we're going to re-graph this, but then we're going to see how does this process change if instead of the minimum value, we instead use the maximum value or circumscribed rectangles. And in this situation, it will be a lot smoother. So it won't be quite as hairy as what we just did. It's still going to be moderately hairy, but not like, I don't know, somebody who's really hairy. Okay. So quick recreation of the quadratic function. All right. 1, 2, 3, 4, 5, 6, 7, 8. So same problem, except now instead of inscribed rectangles, we're going to look at circumscribed, which is equivalent to the right-handed Riemann sum. Oh, not my best work. But we'll live with it. We will live with it. This is still y equals x squared, and we want the area from 0 to 3. So a, or x naught, is still equal to 0, and b, or x sub n, is still equal to 3. I guess I should have put this somewhere else. Yeah, we're fine. So area using circumscribed. Circumscribed rectangles. Right hand. So we're going to start this in the exact same way as we did the inscribed, by saying that the area under this curve can be found by taking the limit as n approaches infinity of some Riemann sum of the areas of some rectangles. And just as before, the area of a rectangle has not changed. It is base times height. And just as before, we are going to allow the base to be this constant delta x. We're going to partition this evenly. Our base of all of our triangles whose area we're going to add together is going to be delta x. And then, just as before, we're faced with this decision of what are the heights of these rectangles going to be? And so this is where getting a little bit of our hands dirty and drawing some rectangles out will be instructive. So whatever our delta x ends up being, eventually we would have a x sub 1. It's important to note that the difference, or the distance between 0 and x sub 1 would be delta x. That's the base of those rectangles. But now we're going to be wanting the maximum value on each of these intervals for our height. So the very first rectangle, this very short rectangle, will have a height of x sub 1. Okay, so let me just see how we'll do a similar chart here to kind of instruct us that we did on the other example. Call it height of rectangle. And I know this seems like kind of strange to be doing this like weird kind of side work, but this is what it takes sometimes. Like, yes, there are formulas, and yes, there is stuff you can try to memorize and cues you can try to remember to put you on a certain path. But at the end of the day, your best tool is your brain and just thinking these processes through. And especially when we get to some volume problems, it's not going to be like a straight line path to some of these solutions. You have to sit there and look at it and visually see what's happening. And so that's why, you probably won't see this in the book. They just say, oh, of course it's f of x sub I. But this is the kind of problem solving process that at least my brain needs. And I think it's important to start to cultivate the ability to be creative in these processes and not just follow, this is the steps the book says. Yes, those steps are helpful. You need to understand where it's coming from. So this height of the rectangle thing is going to help us see what is the expression we actually use for h. So the first rectangle, this first guy, because we're using circumscribed rectangles, we'll use f of x sub 1 as the height. F of x sub 1. Yeah, that's fine. And then our second rectangle, we get to x sub 2. Again, the delta here is just delta x. That's our base. We'll use x sub 2 as our input there. And so then if we just wanted to do some random ith rectangle somewhere in the middle, our ith interval would go from x sub I minus 1 to x sub I. Because we want the maximum value the height we would use for our ith rectangle would be f of x sub I. And so then now hopefully there's a little less resistance to the idea that the height here that we're going to use is f of x sub I, as opposed to the f of x sub I minus 1 that we use for the inscribed rectangles. So this is a big divergence here. This is a difference from the previous process. Now the height is based on f of x sub I.
Why is that? Like, why is this one I and the other one's I minus 1?
Because of the instructions we were given. Because on the last one, they said to use the inscribed, meaning the minimum value on each interval. So that first rectangle, and it was sort of insane, but the first rectangle on that last one had a height of f sub 0, because that was the minimum value on the first interval from x naught to x sub 1. But now on that same interval, the maximum value is at x sub 1. And so you're probably thinking, well, if we're starting with different rectangles, how do we get the same area? Because we will get the same area here. Because when you turn it up to infinity, that very first rectangle is flat no matter what. Whether we're using x sub 0 or x sub 1 as our height, you squeeze those things close enough together, it's the same spot.
Got it. Thank you.
So we're going to use f of x sub I. What I think we're also going to do that we didn't do last time is now look at, okay, what do each of these indexes, what are they actually? Okay. So kind of cut off this table and do well, we'll just start listing them. Okay. So x sub 0 or x naught is 0. X sub 1 is x naught plus delta x. And to get to x sub 1, we're starting at x naught and adding delta x. Okay, but x naught is 0, so this is just delta x. X sub 2 is x naught plus 1, 2 delta x's. Or if you want, you could do, let's actually do it this way. X2 is x sub 1, and then we just move over another delta x. Well, x sub 1 was a delta x, so x sub 2 is 2 delta x's. X sub 3, you start at x sub 2 and go over delta x. Well, x sub 2 was 2 delta x's, so this should be 3 delta x's. Which means if we have x sub I, because that's what we're going to plug in here, what do we think x sub I is going to be in terms of delta x's? We see this pattern emerging.
X sub I minus 1 is delta x.
Well, so yeah, we could do x sub I minus 1 plus delta x for sure. That's literally what it would be. But how many delta x's would x sub I minus 1 be?
I.
So yeah, kind of, let's look at the pattern that's emerging on the edges. X sub I, or x sub 1 was 1 delta x, x sub 2 was 2 delta x's, x sub 3 is 3 delta x's. How many delta x's should x sub I be?
Would it be I delta x?
Yeah, I delta x's, because, and you could just keep going with that logic that x sub I minus 1 is I sub 1 delta x's. We're adding another delta x, and you get I delta x's. So now this can be rewritten as the limit as n approaches infinity of the sum from 1 to n of f of I delta x times delta x. And then this is, I forget who asked, this is where that step's going to come in, where we're going to end up with some more delta x's. Our original delta x from the base of our rectangle, but now we've introduced a delta x as part of the input to our function. And so now we're going to plug I delta x into our function, which happens to be the quadratic function. And so we'll do the limit as n approaches infinity of the sum from 1 to n of I times delta x squared. We're just applying the function f now. The function f is x squared. So this is our input. So this is what comes out. Times delta x. Still hanging around from the base. So now hopefully you can see that this is quite a bit friendlier than the previous example where we had to expand a binomial. This is going to be pretty nice. And I will actually show the intermediate step to kind of make sure we see where the x cubed comes from. This is the limit as n approaches infinity of the sum from 1 to n. This thing squared is I squared times delta x squared times delta x. So this is the result of squaring this quantity. This is just still hanging around from being the base of our rectangles. And so now that gets absorbed into a delta x cubed. So it's the sum from 1 to n of I squared times delta x cubed. Well, delta x cubed is still the same because delta x is 3 minus 0 divided by n. So delta x cubed is this 27 over n cubed. And just as before, this same logic applies, that just looking at this sum that acts only on I, it has no effect on 27 over n cubed. As far as we're concerned, 27 over n cubed is just some constant that tags along for the ride as we square 1, and then square 2, and then square 3, and then square 4, and then square 5, and then 6, 7, 8, 9, all the way to n, and add it together. Each one of those gets attached to a 27 over n cubed, whatever n is, but this does not change at each step of our sum. It's just there for the ride, which means we can just pull this out. And so I'm going to start this back up here. And so what that means is we can write this as the limit as n goes to infinity of 27 over n cubed times the sum from 1 to n of I squared. We'll just then worry about this sum, see what that comes out to, and then only apply the limit once we've only got n's involved that we've simplified down. But again, hopefully you're seeing this case is a lot easier to use the circumscribed. All we're dealing with is I squared. Remember what we had on the last one? We had an I squared and a negative 2i and a 1. We had to expand 3 different sums and simplify them. This one, we're just dealing with I squared. That makes us happy. Or it should. So we get the limit as n approaches infinity of 27 over n cubed. This turns into the n times n plus 1 times 2n plus 1 divided by 6. So this is the limit as n approaches infinity, 27. I'm going to do 2 things at once. 27 over 6 times, I feel like I should have this memorized, but I don't. 2n cubed plus 3n squared plus n. 2n cubed plus 3n squared plus n divided by n cubed. Okay, so I distributed this all out, and then I swapped my denominators because I'm going to want to do this division and see what comes out. But hopefully we're already kind of visualizing that this is going to work out just the same. This 27 over 6 is really just 9 halves, and it has no bearing on the limit. And so we pull it out, and now the limit is going to act upon whatever's left when we divide n cubed into each of these parts of our numerator. So 2n cubed divided by n cubed is like 2. 3n squared divided by n cubed is like 3 over n. And n divided by n cubed is like 1 over n squared. And now only at this final step do we turn this up to infinity. And when we turn this up to infinity, nothing happens to the 2. 3 over n goes to 0. 1 over n squared also goes to 0. And we're left with 2 plus 0 plus 0. 9 halves times 2 is 9. And so we get to the same area, which is sort of fascinating, okay? Or at least let's take a moment to be fascinated by that. In this example, we were starting with approximations that were bigger than our area, bigger than our actual area. And maybe we started with n equal to 10, and we had 10 rectangles that all over approximated, and our volume was too big, our area was too big. Then we started increasing n, and that overestimation got smaller and smaller and smaller. And eventually the limit of that overestimation approached 9. Over here, we did just the opposite. We started with these underestimations at each step, but then as n got bigger and bigger and bigger, and we got more and more triangles, this underestimated area got smaller and smaller until eventually the limit of that Riemann sum approached 9. And so from both sides of underestimating and overestimating, we got to the same spot. It's kind of cool. Which means that it doesn't matter which one you use. Obviously, or hopefully it's obvious, this one was way smoother in this case. That doesn't mean that circumscribed is always the way to go. You have to kind of identify the situation and see what's going on. Questions?
Mr. Smith,
Yes.
is it always going to be that, like, could we use as a rule of thumb that if it's an increasing function, then using the right-handed limit is better, and then if it's decreasing, you use the left hand, or is it just like a case by case?
So we're going to kind of, yes, as a rule of thumb, that's a good approximate. That's a good rule of thumb.
Okay.
Yeah. Okay. So for tonight, again, I'm not going to make the homework due for any of the sections we do this week until Tuesday morning. But if you want to try to tackle, I don't think I gave you that many, but obviously each one of these problems can be pretty time intensive. Let's see, where did that go? I'm trying to find the chapter 4. What problems are left in the assignment? I can't find my assignment sheet. You may have that in front of them.
It's 21, 22, 23, and 37.
Let's see what that looks like. Yeah, so 21 and 22 are literally the same exact thing as example 2 and 3, but now you're just looking at between 0 and 2. But that could be, so that'll be kind of a nice practice to do because you're basically following this, you are literally following the same process. 23 gives you a different curve, so that'll be good to practice. So again, yeah, I would say for sure do 21 and 22 tonight just to kind of get that muscle memory going. And then if you have the time to do it, try to finish the rest of them. tomorrow we will keep trucking and start 4.5. We will probably no ways finish 4.5, but we do need to get that started. And then at the end of the day tomorrow, I'll kind of make the call on maybe splitting 4.5 assignment so that I can assign some of those problems to be due Tuesday. But for tonight, I would say at least do 21 and 22 to just kind of do this on your own and start building that muscle memory. But again, it won't be due till Tuesday. Questions, thoughts, feelings?
Yes. This is for the latest example, but around like the fourth or fifth step, f of I delta x becomes squared. What was the reasoning for that again?
Based on the function. So this step here is like very uninformative or very unspecific. To say that something is f of x sub I, like, okay, but what's f? What's x sub I? So the first thing we did was figure out what's a more useful definition of x sub I. That's what we did here. And we decided, oh, x sub I at every step is just going to be whatever amount of delta x's, I delta x's. Now with that definition of x sub I, we can deal with the f part of this, and the f is based on whatever curve we're looking at. In this case, the curve we were looking at was x squared, and so f was the squared function, and so we took this new definition of x sub I and plugged it into our function, which was x squared.
Okay.
So if this was the cubic function, this would be cubed. If this was 2x plus 7, this would be 2 times I delta x plus 7 times delta x. It's whatever your function is.
All right. Thank you.
Anything else? All right, you guys are good to go, and we'll see you tomorrow morning.
Thank you.
You're welcome.
Bye. Thank you.
Thanks for toughing it out, Hoagland. Oh, hello.
Thank you.
Yeah, I wonder who.
Mr. Smith,
What's up?
did you get me? I was a bit late.
Yeah, you're fine. I was also a bit late, so.
All right, thank you.
Yep. See you tomorrow.